Good evening. Today we're going to talk about section 4.6, linear approximation and differentials. So the entire concept of this is that we can approximate any function we like with a line, and not only a line, but a line tangent to our function at a point. So here I've got this really excellently done drawing. You can thank me all you want, but imagine plotting a smooth curve with the graphing utility. Now pick a point P on the curve, draw the line tangent to the curve at P, and zoom in on it several times. So we go from this outermost zoom into this outermost, into this innermost zoom. As we successively enlarge the curve near P, it looks more and more like a straight line, namely the tangent line. And the fundamental observation that smooth curves appear straighter on smaller scales is called local linearity, and it's the basis of linear approximation. So pretty much, as long as we're close to a point P, we can approximate the points next to it with a straight line. So assume that our function f is differentiable on an interval containing a point A. The slope of the line tangent to the curve at the point A, f of A, is f prime of A, and therefore the equation of the tangent line is y minus f of A, so y minus y1 equals f prime of A times x minus A. Or if we solve for y, we get y equals f of A plus f prime of A times x minus A. And I have a little drawing here for you, right? So the equation of our tangent line describes this line as it passes through this point. And we can see that as we go further to the right, we get further away, and as we go further to the left, we get further away from our graph. And that's okay. The tangent line represents a new function, we'll call it L, and we'll call this the linear approximation of f at a point A. So we just replace y with L in this case. L equals f of A plus f prime of A times x minus A. If f and f prime are easy to evaluate in A, then the value of f at points near A is easy to approximate using the linear approximation L. That is, f of x is approximately L of x, where L of x equals f of A plus f of A, f prime of A times x minus A. And I'll show you using an example, and it'll make a lot more sense then. So here's the definition for you. Suppose f is differentiable on an interval I containing the point A. The linear approximation to f at A is the linear function L equals f of A plus f prime of A times x minus A for x values in your interval I. So let's go ahead and do an example. In this example, we're going to find the linear approximation function to f equals the square root of x at x equals 1. And then we're going to use that to approximate the square root of 1.1 and the square root of 0.1. So this first step is find the linear approximation to f of x equals the square root of x. So what we need here is our linear approximation, which is L of x equals f of A plus f prime of A times x minus A. We know that f of A equals square root of the value 1, f prime of x equals 1 over 2 times the square root of x, which means f prime of A equals 1 over 2 times the square root of 1, which is just 1 over 2. And then we have A equals 1. So we plug all of this in, and we get L of x equals the square root of 1, which is 1, plus 1/2 times x minus A. So it should be x minus 1 here. So that's our formula. We found the linear approximation to f equals the square root of x. And now, for our next step, we just plug and chug. Using our linear approximation, Using our linear approximation, L of x equals 1/2 times x plus 1, we evaluate at 1.1. And when we do that, we get the answer 1.05. So this is our final answer. And now we're going to plug square root of 1.1 into a calculator, and we get 1.0488 repeating. So the linear approximation has an error of about 0.0012. And furthermore, our approximation is an overestimate because the tangent line lies above the graph of f. So the square root function looks a little like this. So a tangent line is going to look like this. And we've got this space above it. And I think I actually have a picture. So at 1.1, the tangent to f equals the square root of x is going to be above the line f of x equals square root of x. And furthermore, it's also going to be above 0.1. That's way over here. And indeed, because 0.1 is further away from 1 than 1.1, we expect our error to be even worse. So using our linear approximation, L of x equals 1/2 times x plus 1, we evaluate at 0.1. I should have changed this. And we end up with the answer of 0.55, where the exact value of square root of 0.1 is 0.3162, which is far less than our approximation, which brings us to my next point. If f is concave up, then our linear approximation will always be an underestimate. If f is concave down, then our linear approximation will always be an overestimate. With this knowledge, suppose we have a linear approximation of f of x equals x to the 1/3, otherwise known as the cube root. Would we expect an approximation to be an overestimate or an underestimate? And the answer comes from the fact that x to the 1/3 is always concave down. It looks something like this. So we expect that when we draw a tangent line at any point, it's going to be an overestimate. So here's a little bit more information, and this will probably become clearer and clearer later on in the course when we start talking about integrals. But it's good to introduce it as early as we can so you have time to get used to the notation. A linear approximation says that the function f can be approximated as f of a plus f prime of a times x minus a, where a is a fixed point and x lies nearby. We rewrite this expression as f of x minus f of a equals f prime of a times x minus a. It's customary to use the Greek uppercase delta to denote a change. The factor x minus a is the change in the x-coordinate between a and the nearby point x. Similarly, f of x minus f of a is the corresponding change in the y-coordinate, so we can rewrite our approximation as delta y is approximately equal to f prime of a times delta x. So, suppose f is differentiable on an interval I containing the point a. The change in the value of f between the 2 points a and a plus delta x is approximately delta y equals f prime of a times delta x, where a plus delta x is within our interval. And that's just our concrete definition. So now I want you to approximate the change using the information we've provided. Approximate the change in the function y equals x to the power of 9 minus 2x plus 1 when x changes from 1 to 1.05. So here we know delta y is approximately equal to f prime of a times delta x. So we need delta x, which is going to be 1.05 minus 1.00, otherwise known as 0.05, and we need f prime of x, which is going to be 9x to the 8th minus 2, evaluated at a, where a equals 1. We get 9 minus 2 equals 7. So delta y is approximately equal to 7 times 0.05 or 0.35. So as we change delta x from 1 to 1.05, we expect delta y to change from, we expect a change in delta y to be on the order of 0.35. Now, there's two related but distinct topics that we need to make a little bit clearer. We need to make them a little bit more precise. And that's the change in the function f of x as x changes from a to a plus x delta x, which is different than the change in the linear approximation, L of x, as x changes from a to a plus delta x. So this is just saying that our function is not the exact same thing as our linear approximation. They're similar, but very different. That being said, let f be differentiable on an interval containing x. A small change in x is denoted by the differential dx. We've changed from an uppercase delta to a lowercase d. The corresponding change in f, our function, not our linear approximation, is approximated right there. The change in f is approximated, right, by the differential dy, so that delta y from L of x becomes dy. And dy equals f prime of x times dx. And that's it for me. If you've got any questions, be sure to send me an email. Hopefully when you do the homework, these concepts will make a little bit more sense.